Hello everybody! This video we will start our introduction to heat engines. We've got a few videos on heat engines coming up. The purpose of this one is to introduce us to the concept and what the pressure versus volume graph, the PV diagram for a heat engine might look like. So we've got that introduction coming up. We'll follow that up with an example problem where we get into the nitty-gritty details of going through one stroke or one cycle of an engine. And then we will follow that one up with a conversation about summarizing those details in a schematic that's a little bit cleaner to look at, and we'll talk about engine efficiency. So that's where we're going. But let's start with this introduction of heat engines. So, general principle. On the right there, we have an animation of a heat engine. We're intaking the fuel, we're compressing it, we're igniting it, then we're exhausting it. Intake, compression, spark and ignite, exhaust. And so we are doing this. This cylinder here is filling up with gas and then exhausting it for the purpose of moving this piston up and down, which has a connecting rod on it. That connecting rod is connected to a crankshaft. And so we are trying to get this linear up and down motion from the piston, which will eventually then become this rotational motion of the crankshaft. But we're going to study this up and down motion of the piston. So, general principles. This needs to be a cyclic process. What we mean by cyclic is that it happens over and over and over again. If you have an engine that only goes forward once and then stops, that's not a very useful engine. It needs to repeat. No one wants an engine that only works for one stroke. Principle number 2, we need to push energy out of the system and into the environment through work. So the connecting rod there needs to we need to push energy into that connecting rod, which is part of that environment. So we need to send energy out into the world from the gas. So we need an output amount of work, W subscript out. We're also going to need to use energy to reset the cycle, but we want to use less energy resetting the cycle than we wanted to send out during that forward stroke. So we're going to need to use energy for a reset. We need to use less energy than we sent out into the world through work. So we need some input work, W in, to reset the cycle, but we want to make sure that that W in value is less than the W out value. We're sending more energy out into the world than we're needing to reset through work. So where is that extra energy coming from? Well, it's going to come from a heating process, which is why we have a heat engine here. And that note there, it's easier to push against colder gas particles because they are slower and colliding less frequently with the piston wall. So we are going to reset the engine, do input work at a lower temperature than we're sending energy out into the world. That'll be at a high temperature. And that way we can make this last principle happen. Let's put that parenthesis in, and let's keep going. All right, so four-stroke cycle is what we're going to look at here. We've got the intake part of the cycle where we're bringing gas into our cylinders. This is an air-fuel mixture. Your carburetor is what mixes up the fuel in your gas tank with some air, and it's bringing it into this combustion chamber here in the cylinder. The piston goes down during this time. That's step 1. Step 2 is the compression. This air-fuel mixture gets compressed as this piston moves back up. There's a spark plug here that fires, which ignites the fuel in that air-fuel mixture. This is at a high temperature, so we're pushing a lot of energy out. That energy came from the heating of the gas. And that's going to be our power stroke, the stroke forward where we're getting our energy out into the world through working. And then we're going to exhaust that gas because we've now burnt up all of the fuel that was in that air-fuel mixture, and we need to reset. We are going to ignore, for our purposes, for our study, the intake and exhaust parts of that. That's just giving us new fuel. What we're really going to care about is that compression, which is resetting the piston, and that power stroke, which is igniting the gas inside of the combustion chamber, inside of that cylinder, and giving us the out amount of work. So we got the out work coming through the power and the input work in the compression. Those are the two stages we're really going to be looking at here. So what does this look like on a PV diagram? That's really the last thing we'll answer in this video. So here's the example. Got our PV diagram here, pressure measured in pascals on the vertical axis, and then volume measured in cubic meters on the horizontal axis. So, state A, we're going to use the word state. It's a thermodynamic way of describing it, is different parts of that cycle are different states. This is going to be the compression state, the low volume state. It's going to be the pressures that are high pressure. We're going to be at a hot temperature as well. So where does a low volume, compressed, high pressure state live on this PV diagram? Let's see, low volume is going to be on the left, high pressure is going to be near the top. So state A is going to be somewhere in here on our PV diagram. Okay, cool. Now we've got our power stroke. Boom. This is a hot temperature. Okay. State B. We've now gone through our power stroke. We're still at the high pressure. And this is going to be an example of something that stays at the same pressure, although it doesn't necessarily need to be the case. So we're going to still be at our high pressure, but now we've expanded. We've pushed through. This is a larger volume inside of that combustion chamber now. In order to keep the pressure constant, this is actually going to be at a hotter temperature at this point. So this is not quite the same cycle that you saw in that diesel engine before. That'd be an Otto cycle, which is a different cycle than what I'm walking you through here. But anyways, we're now at the large volume state, but we're still at a high pressure, so B is going to be up here. And in order to maintain a constant pressure while sending energy out through working, we're going to have to continually input energy through a heating process. So this will actually get hotter as we do this. We want to keep in mind on this graph that we went from A to B and not B to A, so we'll connect those with a line, and we will orient that line with the direction like so. All right, we're now at state B. It's time to reset this thing, but first, if we reset it as is, then the amount of energy it's going to take through work to reset this is going to be the same as we just sent out into the world, so that's not helpful. So instead, the first thing we need to do is decrease the temperature of the gas inside of this combustion chamber. And we're going to do that at the temperature that it's at right now, or at the volume it's at right now. We're going to keep the volume fixed, but we're going to reduce the pressure by cooling this down. So we're at a low pressure now, still same volume. That's going to be this point right here. We want to connect those two. First, we'll mention that we're at a cold temperature. We'll connect those two, and we'll orient that line saying we went from B to C, not the other way around. All right, now that we're at a lower temperature, it's going to be easier to push this piston back into place. And so, because there's less pressure in this gas pushing back. And so the reset working is going to be less than the output working now. So now we're going to go to, so we've reduced the temperature. Sorry, I forgot to say that. We're now at state D. We're going to compress this gas back to where it was. We're still at our low pressure at state D, so we're somewhere around here at this coldest temperature. In order to maintain that same low pressure, we're going to need to continue to remove energy through a cooling process as we go here. We'll connect C to D, connect them with a line, orient that with an arrow, and now we are almost there, but we want to now bring our compressed gas back up to that high pressure so that we can go through another power stroke and send a high pressure stroke out into the world. So we're going to need to heat this a little bit more to go from D back to A to increase that pressure. So that was our compression stroke there. Now we're going to go from D to A, which will be an increase in temperature. That's typically when you're igniting the fuel with the spark from the spark plug. That's what this step is. That's what this step is right here. All right, so that is the summary of our engine cycle. Real quick, now that it's all on the screen to summarize, we started at a high pressure, high volume, or low volume state. We pushed through our power stroke here. After we did that, we reduced the temperature to go to a lower pressure, because when we push the piston from C to D in order to get it back to its initial position, we want the working that we are doing to push it back to be less than the working done with that power stroke. And now we're going to input some heating in order to increase the temperature back to state A so that we can repeat this whole thing. So that is our engine cycle and what it looks like on a PV diagram. The next example, we're going to get quantitative with this, look at a numerical example. That's coming up next. All right, that's it for this video. Signing off.